In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 22. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with identification of cooling class for liquid immersed transformers. It has already been exhibited that heat disposal from large power transformer is thus to be achieved mainly through the cooling principle, which is common to forced as well as to natural heat disposal system. The heat so far been developed in the active part of a transformer, that is core and winding, as well as in other structural parts, is ultimately transferred to the internal cooling media, that is usually oil, and ultimately further to be dissipated through some kind of heat exchanger delivered to an external coolant, which is either air or water, depending on the type of heat exchanger used. Transformer ratings are being determined on the basic criteria of temperature profile of the unit as it coordinates with the operating cooling equipment. The auxiliary equipment such as fans, pumps, heat exchangers are mainly deployed to enhance the cooling system, which is thereby facilitating to enhance the rating of transformer without increasing the unit's physical size. It's the most important point. Thus, the concept of designing of a transformer with having multiple ratings would therefore be implemented as corresponds to multiple stages of cooling. For higher rating transformers, cooling methods and to be designed phenomena would have to ascertain as corresponds to one, applications where to be used. Number two, size and capacity of the transformer. Number three, whether transformer is of multiple rating. Number four, temperature of insulating liquid at the top of the tank. Number five, difference between the top liquid temperature and the external cooling medium temperature. Number six, difference between the winding bottom hub insulating liquid temperature and the external cooling medium temperature. Number seven, hottest temperature of winding conductors in contact with solid insulation or insulating liquid, that is hotspot winding temperature. Number eight, difference between hotspot winding temperature and the external cooling medium temperature. These points to be considered. For higher rating transformers, the heat as carried by the insulating medium cannot be effectively cooled only by providing radiators and fans. To enhance the rate of heat dissipation, it is referred to install oil circulation pumps for circulating oil within a closed loop from transformer tank inside to external heat exchangers where air or water is used as a secondary cooling medium. Transformer, while is being equipped with forced directed insulating oil circulation through the main winding, then the rate of oil flow is to be determined by the pumps only and is quite independent of transformer loading sequence. For general identification of cooling medium and cooling mechanism, some standardization has been made through with a list of code letters by different international standards organizations. Listing of code letters as referred to the IEC 60076-2 in the year 2011 standard for the application of liquid immersed transformers cooling methods is therefore to be explained on an assessment of the temperature conditions as corresponds to heat losses within the transformer unit. Let's see the letter and the description as per IEC 60076-2 2011 standard. Transformer internal cooling medium. First letter cooling medium is when it is written as O as a letter, then insulating liquid with fire point is less than or equal to 300 degrees centigrade. When it is written as K, insulating liquid with fire point greater than 300 degrees centigrade. Letter L indicates insulating liquid with no measurable fire point. Now, transformer internal cooling mechanism. First point is cooling medium. Second one, internal cooling mechanism. Second letter, that is cooling mechanism or process of coolant circulation. N, natural convection through cooling equipment and windings, that is natural thermosiphon flow. F, forced circulation through cooling equipment, but natural convection or thermosiphon flow in windings. D, forced circulation through cooling equipment, directed flow in windings. External cooling medium, that will be the third letter, which is cooling medium. A is air and W is water. External cooling mechanism, that will be the fourth letter, which indicates the cooling mechanism. N, that is natural convection system, or F, forced circulation system. Significance of flash point and fire point of dielectric insulating fluid. Flash point of a liquid hydrocarbon is to be referred as the lowest temperature to which it must be heated to emit sufficient flammable vapor to flash when brought into contact with a flame under specified conditions. Flash point of transformer's insulating fluid thus can be indicated as the lowest temperature at which liquid can vaporize to form an ignitable mixture in air without necessarily maintaining a fire. But the fire point or ignition point of a liquid hydrocarbon would have to refer the temperature at which the oil vapors will continue to burn when ignited. The fire point of a dielectric insulating fluid is therefore be the lowest temperature beyond the flash point at which the mixture of oil vapors and oxygen will burn continuously if ignited. A dielectric insulating fluid of having flash point above 140 degrees centigrade and fire point above 300 degrees centigrade is listed as a less flammable dielectric fluid. Again, I repeat, a dielectric insulating fluid of having flash point above 140 degrees centigrade and fire point above 300 degrees centigrade is listed as a less flammable dielectric fluid. Importance of insulation system for power transformer. just after the construction and commissioning phase are completed. Since then, power transformers are continuously in operation for the electrical energy transmission and distribution system network. Their lifespan would obviously be determined by the ability of the mechanical resistance of their internal insulation system to withstand the short circuit current forces. Hence, insulating material is one of the most critical components of a transformer, and adequate insulation between different active parts of the transformer is necessary for its safe operation during any sort of accidental overvoltages. Electrical energy conversion from one voltage level to another would cause a generation of heat in the transformer. The temperature as developed must have to be kept within limits so that it will not adversely affect the dimensional stability of the insulating materials used in the construction of the transformer. The purpose of electrical insulating materials is to insulate electrical components so as to isolate coil and core from the ground, from the structural part inside the transformer, and at the same time providing mechanical support for the conducting components. The choice of those insulating materials is a fundamental factor to ensure greater efficiency, reliability, and overall operating life of electrical apparatus, as they are always in contact with conductors. Insulating oil is used in power transformer, which has the function both as a dielectric material and heat transfer fluid. So far the power transformer is concerned, both solid cellulose, that is cellulose paper, and liquid insulation, that is oil, would have the ability to withstand the effects caused by the high electrical stress and the mechanical stress as evolved due to overloading, and for which amount of heat to be generated. Therefore, based on the extreme operating conditions, selection of these internal insulation materials must have to be judiciously designed, and that ultimately helps to extend the life expectancy of the assembly of the transformer. Electrical insulation system in a transformer has to be categorized. One, significant type of insulation system that has to be deployed. Number one, between the core and the LV winding. Number two, between LV and HV winding. Number three, between top and bottom of winding and yoke. Number four, between HV winding and tank. Number five, bushings. Less significant insulation system that has to be deployed. One, between the conductors, between the turns of the windings, between the layers, between core laminations, between joints and connections. Important properties so far been categorized for the insulating material as used in transformers. One, very high specific resistance, low relative permittivity. Number three, high dielectric strength. Number four, low dielectric loss. Number five, better thermal conductivity. I have to explain in the note. Number six, better temperature withstanding capability. Number seven, low electrical conductivity. Not. Thermal conductivity of insulating material has an effect directly on the actual cause of temperature rise as corresponds to transformers by determining the thermal resistance of heat transfer from conductor to the ambient. However, transformer design using solid insulation materials with higher thermal conductivity would have been considered as a type of development of the transformer manufacturing process. Now, structural features of the insulating materials for assessing its viability to use, whether it is viable to use for insulating materials to transformers. One, high density, as the rate of heat diffusion and electrical diffusion both have to be depend on mass per unit volume of a matter. Again, I repeat, high density, as the rate of heat diffusion and electrical diffusion both have to depend on mass per unit volume of a matter. Number two, low ignitability, that is fire resistant. Number three, high vapor permeability. Solid insulations possesses small internal air voids, and those are very much hygroscopic. If the material must have a higher vapor permeability, then during heat treatment process, the trapped water can easily be escaped through its pores. Low thermal expansion. Insulating sheet, while placed in a compact space, then any sort of thermal expansion due to change of temperature would lead to various types of mechanical problem. So, thermal expansion value in case of insulating material must have to select as low as possible. Using insulating materials for power transformers of having the properties as mentioned. One, hydrocarbon, mineral oil or synthetic oil, electrical grade paper, that is kraft paper, press board. Number four, wood and insulated wood. Number five, insulating tape. Number six, phenolic laminated paper-based sheet. Number seven, phenolic laminated cotton fabric sheets. Not cellulose-based insulating paper, while puts into the insulating oil under vacuum, it attains extremely high electric strength. That is kraft paper. Basically, electrical insulation is thus to be required whenever there is a perfect necessity of having constant phase of difference in potential between 2 points from the 2 points of the conducting items. Again, I repeat, basically, electrical insulation is thus to be required whenever there is a perfect necessity of having constant phase of difference in potential between 2 points of the conducting items. Most important one, in the majority of power transformers, however, oil of higher dielectric strength with high temperature withstanding ability and the cellulosic insulating materials, that is paper or press board, these two are the usual constituents to act as the most perfect insulating structure. Cellulosic transformer insulation, which includes pressboard or paper, would have to act as a dielectric substance by storing electrical charge while the transformer is at energized condition, and thereby isolates transformer components that exist at different level of voltages. This solid insulation had also made to perform a perfect mechanical support of the windings, as well as would have to contribute better thermal condition of the transformer by creating cooling ducts for the oil to circulate. Such insulation would have to fulfill its best possible performance when it is dry, dirt-free, relatively void-free, and utilized within a certain temperature bandwidth. Cellulosic insulating paper, mostly kraft paper, is used to serve categorically as a minor insulation system which includes wrapping of individual conductors, whereas compressed paper boards are thereby used to serve categorically as a major insulation system which includes barriers, spacers, and clamps, angle washers for mechanical support of the winding. Kraft paper, which refers to a specific type of pulping process, that is from unbleached softwood pulp, that ensures to manufacture an electrical grade paper of better dielectric strength and durability with having low thermal conductivity and has to contribute as a good insulator. Another point, kraft paper has the mechanical property of very low thermal contraction and its elastic elongation at elevated temperatures is quite reasonable. It is obvious that the paper must have sufficient tensile strength so as to withstand the tension exerted on it while wrapped over the individual conductors. It should also be able to sustain several types of thermal stresses as developed during certain abnormal operational sequence of the particular transformer. Dry cellulose, that is pressboard or paper, as an insulating material that can have small internal air voids which ultimately would have to affect its natural insulating strength as well as heat dissipation criteria. But as the oil-filled power transformer always have to fulfill a composite type of liquid solid insulation structure, where the voids of the cellulose insulating materials are thus become totally impregnated with oil, resulting in an improvement of both the insulation strength and the heat dissipation capacity. For high rating transformers, oil impregnated kraft paper of high permeability or even thick pressboard is mostly provided as winding interlayer or disc to disc insulation. Pressboard is also meant for numerous other applications such as top and bottom coil clamping, ring block, spacers, angle washers, yoke insulations, etc. Insulating criteria of oil and paper both are the most important components to ensure optimal operation of a power transformer, and their actual conditions may have to determine the lifespan of the transformer. degradation of transformer oil and paper insulation under selective conditions. First of all, air ingression, moisture and oxygen. Obviously, some metallic substances, fibers, etc. with impact of temperature. Oil, at the same time paper, some thermal degradation. For mechanical stresses, insulating paper aging. Number 2, degradation of polymer main chain caused by thermal stress. Number 3, moisture droplet buildup. Number 4, loss of tensile strength. Number 5, fibrous products. Whereas electrical stress, oil degradation due to acidification and contaminants. Oxygen and water, gas with contaminants. These two processes are actually responsible for oil degradation as well as insulating paper aging system. Now oil and paper thermal degradation happened. Temperature excursion, deviation from design value. And in case of oil degradation, thermal faults, overheating, short circuit, electrical discharges, oil is affected with increasing voltage stress. And these two will happen mostly due to certain electrical stress and mechanical stress. And the resultant, 1, breakdown of oil with gas bubble. Number 2, increased thermal conductivity. The degree of moisture ingress and the aging phenomena of the insulation system in the windings are the most crucial elements to ascertain the technical life of the transformer. Kraft paper as dielectric material is actually made from plant's cellulose, which originally contains around 5% of water, and after having certain drying process, that level would have to come down less than 1%. It is also to be noted that the transformer oil, while at the presence of oxygen and humidity, would have to oxidize, and that will force to create free radicals, acids, and formation of sludge. At the same time, the degree of thermal degradation of the cellulose insulation material has to upsurge the electrical conductivity and dielectric dissipation factor, and thus this has to weaken the electrical strength of the intra-winding insulation system. However, it is commonly recognized that the insulation system constituting the intra-winding insulation transformers is thermally improved insulating cup type paper saturated with insulating mineral oil. Exhibiting any incidence of hotspot temperature inside winding of the oil immersed power transformer, that would therefore be the most instigating evidence of causing abnormal thermal stress which intends to aging of insulation system. Thermal resistance therefore be the basic criteria for selection of the insulating material as corresponds to degree of temperature what to use, and is defined as the ratio of the temperature difference between the two phases of a material to the rate of heat flow per unit area. Therefore, thermal resistance determines the heat insulation property of the dielectric material. So, it can be concluded that the higher be the thermal resistance, the lower is the heat loss. Using kraft paper as dielectric material has the thermal resistance of only up to 105 degrees centigrade, which obviously not sufficient to insulate high capacity transformers. In this context, transformers, while specially designed to operate at high degree of temperatures, is always be recommended for using synthetic insulating materials such as Nomex Aramid Paper, Nomex Aramid Paper and tapes, adhesives and non-adhesive type. Characteristics and features. Characteristics of Nomex Aramid insulation paper is made of aramid fiber of high tenacity. Aramid fibers are basically of man-made high-performance fibers having with molecules that are characterized by relatively rigid polymer chains. Molecules are linked by strong hydrogen bonds that transfer mechanical stress very efficiently, making it possible to use chains of relatively low molecular weight. Features. Thickness of Nomex Aramid insulation is of the order 0.05 to 0.76 millimeter. Width 20 to 965 millimeter. Number 3, high durability. Number 4, high mechanical stability. Number 5, high thermal stability. Number 6, highly resilient. Number 7, low rate of deformation. Number 8, moisture resistant. Number 9, heat resistant. Number 10, flame resistant. Number 11, chemical resistant. Number 12, radiation resistant. Number 13, high dielectric strength. Desirable qualities of high voltage insulation. Nomex Aramid paper offers dielectric strength of above 10 kb per millimeter without being treated with insulating varnish or resin, and can have to withstand short-term electrical stresses of 18 kb per millimeter to 34 kb per millimeter. However, just to minimize the risk of partial discharges, that is corona, the designers would recommend that the continuous electrical stresses within the transformer must not exceed to a value of 1.6 kb per millimeter. It has to provide C class of insulation, of having outstanding thermal stability of a lifetime over 20,000 running hours at 220 degrees centigrade. Dielectric constant or permittivity is implied to determine the ability of an insulator to store electrical energy. That is, it is a measure of how well the insulating material will act as a dielectric capacitor. It is obvious that the high dielectric constant of a material has to indicate that the material is highly insulating. Dielectric constant has no unit as it is the ratio of two like entities, whereas the unit of permittivity is farad per meter. Dielectric constant and the magnitude of the dielectric permittivity of Nomex Aramid paper would have to increase with rise of temperature but have to decrease with rise of frequency. As the dielectric constant of Nomex Aramid paper is much lower than that of the impregnated cellulose insulation paper. So in this case, the electric field would supposed to be evenly distributed. Now, dissipation factor. Dissipation factor of an insulating material is defined as the reciprocal of the ratio between its capacitive reactance to its resistance at a specified frequency. Dissipation factor of a material can also have to measure the basic tendency of the material to dissipate internally generated thermal energy, that is heat, resulting from an applied alternating electric field. So, material of lower dissipation factor has always intended for dissipating less of its internally generated thermal energy. Typical electrical properties of Nomex Aramid paper so far been exhibited. 1. Rise of temperature would have a minor effect on dielectric strength and dielectric constant. Number 2, variations in frequency up to 10 to the power 4 Hertz have essentially no effect on its dielectric constant. At 50 Hertz frequency, dissipation factors of thinner papers of thickness 0.05 millimeter are essentially be the same as those of thickness 0.25 millimeter at temperatures up to 200 degrees centigrade. However, at higher temperatures, that is more than 200 degrees centigrade and frequencies, dissipation factors of the thicker papers of thickness more than 0.25 millimeter would have somewhat found to be higher. Number 5, voltage endurance level is quite superior to other commonly used organic insulations as well as insulations with some inorganic compositions. So, insulation made of Nomex Aramid paper may not fail prematurely under any sort of occasional overvoltages that may have to produce brief corona discharges. For thinner grades of Nomex Aramid paper will have slightly lower thermal conductivity as compared to thicker grades which will have higher thermal conductivities. Nomex Aramid paper sheet material is made of aramid fiber of high density, smooth surface, good toughness, high tensile strength, and tear strength. As it constitutes with strong hydrogen bonds, so its chemical stability would have been much more compatible to use with all types of transformer fluids such as mineral and silicone oils and other synthetics. It has also to ensure its stable structure with having excellent electrical and mechanical properties of sustaining a superior resistance quality to some chemicals such as most of the inorganic acid, most of other chemical reagent and organic solvent. let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want to know, then let me suggest or let me inform in the comment section. Thank you. Thank you for patient hearing.